Hey everybody! In this video, we will be talking about Hess's law. But before we begin, let's review what delta H is again. Delta H is the heat absorbed or released by reaction at a constant temperature. And in chemistry, we usually always associate delta H with a mole of reaction. And if we don't care about the quantity, such as if we don't care whether it's a mole or not, then we just stick to Q instead of delta H. But typically when you have a reaction, you will have a corresponding delta H that will be written in terms of energy per mole of reaction as seen over there. So in this example, CH4 methane is reacted with oxygen gas to form these two products. Of course, this is a combustion reaction. And let's see how this mole of reaction works. So 1 mole of reaction, or just the reaction itself, means that when either 1 mole of methane is consumed or when 2 moles of H2O is produced, then 882.0 kilojoules of energy is released. So this reaction is telling you that either when this amount is consumed, aka 1 mole of CH4 is consumed, or if 2 moles of water are produced, then a total of 882.0 kilojoules of energy is released for that reaction, and that's why it's per mole of reaction, since we are directly referencing the reaction and its coefficients. So now that we've talked about that, let's talk about something special. This reaction illustrates combustion, as I just said. Therefore, the change in enthalpy can be specifically called the delta H of combustion, shortened to Hcomb, and we use this to talk about the change in enthalpy when 1 mole of a fuel, like methane, is burned. Since the coefficient in reaction for methane is 1, this reaction describes the delta H of combustion for methane. So for the delta H of combustion, you always have to remember to make it so that the fuel is 1 mole in the reaction, such as over here, where the fuel, which is methane, which is being burned, has a coefficient of 1, meaning that 1 mole of it is burned, since delta H is referring to the reaction. So now let's do a practice question. What is the reaction that describes the delta H of combustion for C2H6, or ethane? For this, we need to make sure that our fuel, ethane, is going to have a coefficient of 1, which represents 1 mole. And since delta H of combustion is describing the change in energy when 1 mole of fuel is burned, this makes sense. So we gotta make sure that that has a coefficient of 1. So you can start off by just balancing it normally, and it looks like this. But notice how the fuel has a coefficient of 2, and we want it to be 1. So how do we fix that? Well, if you divide all the coefficient by 2, aka just cutting everything in half, cutting the reaction in half, then you get this. And notice how the coefficient on our fuel, C2H6, is now 1. And notice how we have fractional coefficients. Now that's perfectly fine, because you can have 7/2 of a mole. Because remember, a mole is 6.022 times 10 to the 23rd molecules. So taking 7/2 and multiplying by that will give us a whole number of molecules. So we're not cutting molecules in half. We're taking parts of a mole, and a mole is made up of tons and tons of molecules. So putting fractions as our coefficients is fine. So this would be the reaction that best describes the delta H of combustion, since this reaction specifically shows 1 mole of fuel burning. So now that we know this, let's talk about what exactly a fuel is. Well, when you burn things, the fuel usually has a carbon in them. So for example, C2H6, C3H4, and even C6H12O6. All of these are considered fuels, and they can all undergo combustion under certain conditions. So now let's talk about Hess's law. Hess's law states that when you add two or more reactions together, the sum of the delta H's of the reactions is equal to the delta H of the net reaction. So in this example, we have two reactions that we are going to combine, and our goal is to find the net reaction of this. So how would this work exactly? Well, adding reactions together is just like adding algebraic equations together in a system of equations. You simply add both sides together and kind of combine them, and things that are the same on the left and the right will cancel out, while things that are the same on the same side will combine. So, in order to show that, let's look at these two reactions combined. If we combine the left side, we will be left with CO, and this should be in the gaseous state, sorry for messing that up, and we will have 1/2 O2 plus 1/2 O2, which is going to be 1 O2. Now on the right hand side, we have to add up all the chemicals on the right side, so on the right side we will have CO and CO2. Now, what's the same on the left and the right? Well, 1 mole of CO is shared on both sides, so you can cancel out the CO on both sides, because if you think about it, this reaction is producing CO, and immediately after it is being consumed. So 1 mole of CO is produced, and immediately after it is consumed, it's as if it didn't exist in the first place, even though it did exist. But in the net reaction, it's as if it came and went. So that means that our final reaction will be 1 mole of C plus 1 mole of O2 to make 1 mole of CO2. So here we are. This is our net reaction. And notice that by adding these two reactions together, you can also add their delta H's together to get the delta H of the final reaction. So negative 111 kilojoules per mole of reaction plus negative 282 kilojoules per mole reaction gives you negative 393 kilojoules per mole reaction. So Hess's law is practically easy to understand once you do a few questions, but the harder part about Hess's law is actually understanding why it works. So we are going to talk about why this works. So H, or enthalpy, is a state function, so each chemical will have a certain amount of enthalpy, or you could think of enthalpy as the energy of the chemical. Now, if we have CO2 down here, no matter where it came from, CO2 will always have a certain amount of enthalpy, and that's what it means to be a state function. So, now that we are armored with this knowledge, we can take a look at the reaction. So, above over here, no matter how the C and the O2 we started with goes, whether it wants to go straight to CO2, such as here to here, or if it wants to mix the C with half of the O2 to get CO first, and then get the CO and mix it with the last half of the O2 to get CO2. It doesn't matter what path you take, because in the end, the net result is that the C and the O2 are going to become CO2 in the end. So I think this concept is a little easier to understand using a diagram. We start with carbon in a form of graphite, which is apparently the natural form of carbon, and O2 gas. So, no matter what path the C and O2 want to take to get to CO2, the final product, the CO2, will have a much lower enthalpy than the C and O2 combined. But note that the difference between the enthalpies of CnO2 and CO2 will always remain constant. according to this diagram, since the CO2 is placed with less energy while the C and O2 are placed with having a higher amount of energy. So this difference, this gap between enthalpy is going to stay constant. But this difference in enthalpy is the same between the C and the O2, no matter what path the C and the O2 take to get to CO2. So in this green part, notice how the C and O2 first start off by wanting to make CO, and this occurs when C and half of O2 combine, and then from here to here, the rest of the O2 is combined with the CO in order to get CO2. So the big picture is, no matter what path the carbon and the oxygen gas take to become CO2, the path they take will have altogether a same change in enthalpy, and if they take multiple paths to get to CO2, then those individual paths have a certain amount of delta H, and those delta H's combined together will equal the full path that they take if they decided to go straight from CnO2 to CO2. So I'm going to read this explanation to see if this makes more sense. So no matter what path the CnO2 take, it is going to become CO2 in the end. Therefore, the change in enthalpy for each of the two reactions combined is equal to the change in enthalpy for the one-step reaction, since they both lead to CO2. Since the one-step reaction is considered the net reaction, then the delta H's of the individual reactions combined add up to the delta H of the net reaction. So now let's talk about what happens to the delta H when you manipulate the reaction. So in this reaction, I generically labeled A plus B reacts to form C. So this delta H is equal to X, which is a variable. Now, if you multiply all the coefficients by a factor, the delta H is also multiplied by that same factor. So in this case, I decided to multiply everything by 2, so that 2 moles of A plus 2 moles of B make 2 moles of C. And notice how the delta H is also doubled, so now instead of being X, it is 2X. Now what happens when you flip the reaction? Well, A plus B becomes C, has a delta H of X, and if you flip it, C decomposes to form A plus B, then the X will be negated, or in other words, the sign on the delta H will switch. Now, there's an easy explanation for why this happens. So, the C over here has X joules more energy than A and B, because if the X is positive, then that means that C must have a higher enthalpy than A plus B, since the delta H means the enthalpy of the products minus the enthalpy of the reactants. Now, if we switch that up, then we could also say that A plus B has an enthalpy that is X joules less than C. So since this side is less than this side, then this will be X joules less than this side, so therefore the change in enthalpy will be minus X. So hopefully that explanation was not very confusing. So why do we manipulate reactions? Well, we do that in order to get the desired net reaction whenever we add the reactions up. And by doing that, we are able to find the delta H for a net reaction via Hess's law. So now that we're done talking, let's actually do a practice question. And this one's from the Chemistry Olympiad, which means that it is going to be a bit challenging, but we can do this. So before we begin, note that the not symbol, it looks like a degree symbol, stands for standard conditions, which is 1 atm, 298 Kelvin, typically, and 1 molar. Now, you don't have to know what molarity is right now, so don't worry about 1 molar. Now, this is different from STP because STP is at 1 atm and 273 Kelvin, so they're different. So let's read this question now. What is the delta H naught of the reaction for the fermentation of glucose as shown below? So we don't know what the delta H of this is, but we know the delta H is for these three reactions. And based on what we've learned, I'm thinking that we should do Hess's law in order to add up these reactions to get a net reaction that looks like that. So we have 4 answer choices, so that's nice. So now let's think about how we can make the reaction above. If we want C6H12O6 to be on the left-hand side, we have to choose a reaction where the C6H12O6 is on the left-hand side. So over here, it's on the left-hand side, so it's good. So let's copy that reaction down, and since this has a coefficient of 1 and this has a coefficient of 1, I think that we are on the right track. So C6H12, well actually let me use the color black, C6H12O6, and before we continue, I want to point out something very important. When you combine reactions together and you combine chemicals together, make sure that they are in the same state. So if they're not in the same state, you cannot combine them. For example, if H2O gas and H2O liquid were on the same side, you can't say 2H2O gas because gases and liquids are different, so you would have to keep them as separate chemicals. So just keep a note of that, and I don't think that would be a problem here, but let's just move on. So let me just copy down this really long reaction, 6CO2, and let me actually erase this and rewrite it because I don't think I gave myself enough space for this question. So gotta write, and it's going to be very boring to watch this, but we are almost done. So we are done now. So what's next? What other reaction might we add? So if you notice on this side, there are 2 C2H5OHs. So we need to find a reaction that has 2 moles of C2H5OH on the right-hand side. Now, none of these reactions have that on the right-hand side, but this first reaction has it on the left-hand side, and it's only 1, but we want 2. So I think what I want to do is I want to flip this reaction and double it. Now, I forgot to write the delta H for this reaction, but since we didn't do anything to this, the delta H naught of this reaction is going to stay the same, negative 2805.0 kilojoules per mole, and you can write the reaction if you want. Now for the second reaction, remember I said we want to flip this and double it so that the 2 C2H5OHs are on the right-hand side. So let's do that. So over here, as you can see, I flipped the reaction and I doubled all the coefficients. So when you flip a reaction, you have to switch the sign. So if it's negative here, then it must be positive here. And since I doubled everything, then I must multiply the delta H by 2. And I end up getting positive 985.2 kilojoules per mole. Now what do we do with the third reaction, assuming that we need it? Well, let's think about this. There are no useful chemicals in here that we can really use, per se, but we have to think about this in terms of canceling out what we don't want. So I noticed that there's this chemical here, CH3COOH, that I don't really need because that's not in the net reaction that I'm trying to go for. So I have to cancel this out somehow, and that means that there must be 2 CH3COOH on the right-hand side. So far we don't have that. So what can we do to have that? Well, notice how we haven't touched this reaction yet. If we flipped this reaction and we multiplied all the coefficients by 2, then we would have 2 CH3COOHs on the right-hand side. So let me show you how that looks like. So over here, I demonstrated how if I used reaction 2, I flipped it and I multiplied everything by 2, then it would work out. So what happens to the delta H? Well, if we flip it, the negative becomes a positive, as shown right there, and we doubled everything, so therefore we have to multiply the delta H by 2. And when we do that, we get 1748.4 kilojoules per mole. Now, the final part is to see that when we add this up together, will it yield the final reaction? So, let's try to see what happens when we add up everything, and maybe, miraculously, everything will cancel out. And usually, when you do Hess's law, if you're given the right types of equations, they tend to cancel out pretty effectively, and especially for this question, since it's a multiple choice, they make it so that things cancel out effectively, and it doesn't require as much thinking as you might think it needs initially. So, let's add all the reactions together. Now this might be a lot, but let's see what cancels out first. So, first, I know that the CH3COOH's will cancel out, so 2 on the left and 2 on the right are gone. Now we have to think this in a very special way. Notice how there's 6 O2's on the left and 6 O2's on the right. Well, 2 plus 4 is 6, so that cancels out. Now, does the CO2 cancel out? Well, let's find out. I don't think they're supposed to cancel out completely, because there's supposed to be 2 left on the right-hand side. So, what we can do is that we know that there's 4 on the left and 6 on the right. So 4 can be canceled out on both sides, and 6 minus 4 moles of CO2 leaves 2 moles of CO2. Now, what about the water? Well, let's take a look at if water cancels out anywhere in the equation. Notice how 2 H2O's and 4 H2O's are on the left side, and 6 H2O's are on the right side, so that cancels out. And what we're essentially left with is that C6H12O6, and let me do this in a different color actually. So this chemical breaks down to form 2 CO2 and 2 C2H5OH. Notice that every other chemical is canceled out, so we don't include those. So it looks like the net reaction is reflected in this reaction over here when we decide to add up these 3 equations that we created. So it worked out perfectly. So because all this adds up to C6H12O6 solid becomes 2 CO2 gas plus 2 C2H5OH, then that means that we could use Hess's law, which states that the sum of the delta H's of the individual reactions will add up to the delta H of the net reaction. So let's get going and do that. So upon adding up the 3 delta H's, I end up getting negative 71.4 kilojoules per mole of reaction, and that means that the answer is A. And notice that the mole to the -1 is the same thing as dividing by moles. So this is Hess's law, and at first the amount of chemicals might be overwhelming, but if you think about it in terms of what should be on the left and what should be on the right based on the net reaction, as well as what you need to cancel out to get the net reaction, then things typically go fine from there. And if things are not fine from there, then you just have to think of another strategy to use Hess's law. So it's a lot of planning, and eventually, hopefully, things work out. So that's all for this video. Have a nice day.